All right, thank you for joining us today. This Tech Talk series focuses on D&D topics relevant to the D&D EM complex. This event is sponsored by the U.S. Department of Energy, Environmental Management. Please allow me to introduce our Director of Research, Dr. Rio Lagos. He is the Associate Director also at the FIU Moss Department of Construction Management and Director of Research here at FIU Applied Research Center, and the Director of FIU Science and Technology Workforce Development Initiative, also known as the DOE Fellows Program. Since 2012, Dr. Lagos has been the principal investigator for the DOE FIU Cooperative Agreement, conducting multidisciplinary research in the areas of robotics and remote systems, AILM, generative AI, cybersecurity, natural language processing, radiochemistry, environmental chemistry, and decommission. So please join me and welcome Dr. Rio Lagos.
Hey, Walter, thank you, and thank you everyone for joining us. So I have the pleasure of introducing, right, a couple of my colleagues here at the Applied Research Center working in the D&D area. We're going to have two presenters, so Joe Sinicrope and Melissa Komenakis. Both of them will be presenting the topic this afternoon, as you see there listed on the presentation. So first, Joe, let me introduce Joe. Most of you know Joe. So he's been working for us since 2015. He's been concentrating in the areas of D&D, and primarily he's been working with operational testing, evaluation, and deployments of COTS-based technologies in support of DOE EM. Since 2015, he has concentrated on adapting commercially available intumescent technologies as incombustible fixatives and addressing critical enablers such as standard development and regulations to facilitate their acceptance, adoption, and diffusion within the DOE complex. In addition, Joe serves as the chairman of the ASTM International E10 03 Subcommittee on Radiological Protection for the Activation and Decommissioning of Nuclear Facilities and Components, where he oversees a subcommittee under that charged with the management and development of standards, specifications, and testing practices related to D&D. Again, contributing to the D&D community as a whole in the areas of standard development and technology testing, evaluation, and deployment. Also, Melissa, she's a research analyst here at the Applied Research Center. She received her BS in biological engineering from the University of Florida. Yay, go Gators. And she's currently pursuing a PhD in material science at FIU's Department of Mechanical Engineering. And her topic for her research in the PhD program is what she's doing also as part of the DOE EM Cooperative Agreement. She currently supports the activation and decommissioning technology development, testing, and evaluation of fixative materials under the DOE Cooperative Agreement. And she's also a member of the ASTM E10 Committee on Nuclear Technologies and Applications. So it's a great pleasure to turn the floor over to Joe, Melissa, Joe, and they'll go through the presentation this afternoon. And as Walter says, I believe the questions will be held until the end of the presentation. So with that, I'll turn it over to you, Joe and Melissa, and we're happy to have you. We're looking forward to your presentations.
No, thank you very much to Leo and Walter for the great introduction. I'll just kind of follow in Leo's. I've got two kids who are actually graduated from Florida State, the Seminoles. And then, of course, I've got my youngest two kids getting ready to go to the Gators. So I guess I'm both ways on this particular effort. But thank you, everyone, for your time. I know it's valuable, and so we'll try to make this short and to the point. It'll take us about 30 minutes. Although I know we have a question and answer session at the end, I would encourage anybody to preempt that and I'll ask any questions that you may have as we go along. And with that, today's topic's probably a little unorthodox in terms of what you usually hear in terms of a tech talk. So very frequently, as we've been doing this initiative that Leo initiated, and then of course Walter has implemented and executed over the course of the past year, there's been a heavy emphasis and focus on the technology itself. What type of technologies can we bring into the field to deploy to the various DOE EM sites to facilitate whatever the particular problem set is at the time, whether it's robotics, whether it's decommissioning, whether it's legacy management, whatever that particular problem set is. But what we're going to pitch today is that there is a critical parallel development effort that should be pursued in all technology development programs. And that parallel effort focuses on a parallel development of critical enablers. And in this case, we're talking specifically about consensus standards development for the technologies that we're pursuing, and any pursuant regulation updates that may be required as you begin to look at those more mature technologies that are prepared and ready to deploy into the field. And so with that as a brief introduction, we'll go ahead and I kind of like to start off, like I said, I prefer kind of the dialogue format, and we'll start with an informal survey. So we're going to engage the audience here to kind of set the scene. And we've been doing this informal survey since about 2018 or so. Each time that we go to waste management, for example, or to the ANS conferences or various other opportunities, IAEA workshops that we conduct here, and we kind of present two different scenarios. And so I'm going to request that the audience out there, if you can, just input in chat. And if you look at scenario 1, that's that first kind of bullet set, it says choose between two fixative technologies based solely on the information that you have. And so you got two choices. Technology 1, obviously kind of centered on the main line of research activity that at least I pursue under my research portfolio. Incombustible fixatives intended to go into a facility and maintain the stabilization of residual radioactive material when exposed to a variety of contingency scenarios, fire, impact, etc., that are outlined in certain safety basis documents. This particular technology, for technology 1, costs 75 cents per square foot, and it's met a various number of fire test standards from independent testing agencies. So that's option 1. And then, of course, for technology 2, exactly the same type of technology with not having met or not being certified in any particular standards. And so I'll throw it out there to the audience, just kind of input in the chat. Which technology would you choose? Technology 1 or technology 2? And then as you're doing that, in the same chat, between the two, in the second scenario, identical, except in this particular scenario, technology 1, which is the one that comes with the standards, costs $1 per square foot as compared to technology 2 without that effort, but it only costs 75 cents per square foot.
So far, we have everyone choosing technology 1.
Technology 1. And so you're not alone. So we'll add your statistics to our overall kind of ongoing informal survey. And you can say over the course of the last 6 to 8 years that we've been conducting this survey, in scenario 1, 242 folks, plus however many have entered here today, chose technology 1. Identical technologies, except one met consensus standards that have been outlined for that particular technology. And even in the scenario 2, where the technology 1 cost literally 25% more per square foot, I think we're getting generally the same responses. We've had 6 cheap states out there across the last 6 years that decided they weren't going to spend the extra 25 cents. But in general, you can see overwhelmingly consensus standards impact the decision-making when it comes to the technology selection. And this is particularly true as we have conducted our research in safety critical, risk adverse industries such as nuclear decommissioning, where you have significant safety constraints, rightfully so, that are on you. And so this is kind of the scene setter to kind of hit you right up front of the importance. Most people out there couldn't tell me what ASTM E84 are or UL 723 are, but intuitively, you jump in and know that that is the technology that you want. So that kind of sets the stage for why we pursue a parallel development effort in our incombustible fixative research activity and contribute a significant amount of time as well to the development of consensus standards and the testing protocols that go along with those. In other words, we pursue a holistic approach because we've come to realize that that parallel development is absolutely essential. And I think that this cartoon kind of depicts it perfectly. I love these two cartoons so much. I literally spent $50 of my personal funds to get the licensing fee so that I could include them in educational presentations because they really hit home. They hit and reinforce the message. If you look to the left, as a researcher myself, my collaborators at Savannah River National Lab, Idaho National Lab over the years, and some of the other areas, the researcher perspective when it comes to the sites and the end users is kind of this, no thanks, we're too busy for any type of technologies. And so that's kind of the researcher perspective. We're building these great things, we're developing these great technologies, but they just don't want to take them on board. The end user reality is, and what I think kind of emphasizes the point that we're trying to stay here or state and reinforce in terms of a holistic approach, is if you see the mom there, they're kind of like, hey, great invention, but not without inventing the helmet also. In other words, the technology itself is the wheel, but the helmet represents all of those critical enablers that are absolutely essential to getting that technology into the sites, to the end users in their hands, consensus standards and regulation updates. So as we move forward, I was once told when I was a Marine, go ugly early, I'm going big up front. So those are my two most impactful, simple slides that kind of send home the message. But as we go through, we also have a case study. And so as many of you out there know, you were participants in this particular effort where we developed or at least adapted commercial off-the-shelf intumescent coatings and turned those into viable incombustible fixatives, specifically fixative technologies that had the capability of still stabilizing and immobilizing residual contamination, even when subjected to certain thermal, really extreme thermal stressors. But as we went through that process and we actually were successful at getting it into the entry hood of SRS 235F pump facility, as well as process cell number 7, we did our after action with the site. And what came out of there, without a question, some of the comments that were highlighted was that the holistic approach that was pursued in that research activity, focusing on the technology itself, but not neglecting those critical enablers, and that it was really the critical enablers that provided a significant return on investment and value creation in facilitating that technology's integration, acceptance, qualifications with the safety basis personnel, etc., and facilitated its ultimate deployment into the PUP facility and now throughout SRS 235 overall. In other words, not just about the technology, but about those critical enablers as well. And so as we went through this, we kind of highlighted a couple of efforts. Many people have seen Roger's theory of technology diffusion. This is kind of our modification of that. We've all heard of the chasm right here that you have to cross, and we really kind of address there are two specific kind of human factor drivers, but real efforts that must be addressed as well. Risk. Critical enablers, specifically consensus standards, significantly mitigate the risk. And then you need to also do that human factor component of incentivize the end user to use it, the particular technology. In our case, fixative technologies, but this model, I would say there are critical enablers associated with every technology development out there, identifying what those particular enablers are and integrating them into your holistic technology development program and process will pay significant dividends. And as we put here for the standard specifications and testing protocols, what they really do, and we'll go into it in greater detail, is they mitigate the impacts of information asymmetry. The researcher knowing more about the particular technology than the end user, so it closes that information asymmetry gap. And then, of course, we'll go into the regulation updates and how standards can link into that particular process as you move forward in your efforts. So we're going to bring up the next slide. Perfect. And so here's kind of there's a significant body of literature that supports the role of consensus standards in promoting technology innovation. That little picture off to the right was part of my thesis that I wrote on this particular topic. I wish that were true. It's not at all. It's actually an extract from a seminal document that was written to demonstrate this from H.E. Leland, as you can see there, that kind of Nobel laureate type effort that really demonstrated empirically the positive impacts of minimum quality standards in a consensus sense and uniform testing protocols on mitigating that information asymmetry. Quacks, lemons, and licensing, a theory of minimum quality standards. And it was, as he demonstrated, mathematically particularly advantageous in highly risk-averse industries. But the literature isn't just academic in nature. You can see that there are GAO reports that have come out, specifically the GAO report on DOE's program to develop new technologies for environmental cleanup, where they highlight specifically the importance of kind of addressing these critical enablers and really explicitly state the importance of consensus standards. And then, of course, public law itself kind of supports this idea and outright mandates that the federal government, through Public Law 104 and 113 and their circular A119, that federal participation in the development and use of voluntary consensus standards is kind of mandatory, and that there should be this participatory effort to facilitate technology development and acceptance and diffusion into whatever the particular problem set is that we're dealing with. And the reason is that it addresses the whole host of stakeholder equities. Consensus standards address the concerns of policymakers and regulators, end users, the producers and manufacturers in the industry base that is utilized in making the products, and of course the public interest as well. Consensus standards is one of those initiatives and efforts that brings in stakeholder representation and stakeholder interest and finds a consensus in how these particular efforts can be done, from establishing the performance requirements and compliance oversight for the policymakers, to reducing the risk and instilling confidence and trust and improving the technology selection process for the sites, to clearly telling the producers what it is they need to develop and build, to, of course, giving the public that sense of overarching security, openness, and transparency, and common understanding for the particular technologies being utilized. So these are all the various stakeholder equities that are addressed through the consensus standards process. And so we pitched this, and overwhelmingly, obviously, DOE EM, Jennifer, Rod, Kurt beforehand, Andy, the whole host, we have representatives from across, have been exceptionally supportive of incorporating and integrating this component into the overall technology research activity portfolio. And so as you go through here, you can see some of the comments, starting with Andy. Many of us have been around for a while in this. You can see his comments on, kind of there's this general acceptance. This was kind of centered primarily on fixative technologies, this intuitive sense, but the need to formalize the process. And that's what consensus standards do. It was outlined specifically in the AAR the after action review that I articulated in the case study from the SRS 235F successful deployment. And then recently with Rod Raimondo during our robotics conference, where he said, hey, a critical component is to confirm that the technology works as advertised, and a recognition that these components are important and that consensus standards facilitate that particular integration. So with that, we've stepped out. We have engaged with ASTM International's E10 committee, which is on nuclear technology and applications. I'm the vice chair for that particular committee, and then actually chair the E1003 subcommittee, which is specifically charged with the development of standard specifications and test methods, testing protocols, practices, etc., for technologies intended to be used for D&D activities. And so this ASTM E1003 subcommittee kind of has oversight on a whole host of different types of technologies intended for D&D purposes. And we have been obviously centered, selfishly so, I guess, particularly because of my research activity on fixative technologies, but it is not limited to that. If you have robotics that want to be deployed, and we're at that stage where you're ready for the industry at large to begin a process of developing robots across the board, that would fall under my charge in E1003 subcommittee. Any of the other types of technologies that we utilize across the complex would kind of fall into that. And we focus on developing specifications, specifically an explicit set of requirements to be satisfied by that particular technology, whether it's a material, a product, a system, or a service, and then the corresponding test methods, practices, and protocols to ensure that that particular technology does that specific requirement. Our E1003 subcommittee has about 45 members, really from across the international D&D community. We have significant representation from Japan, from Europe, from Norway, from Sweden, from Germany. But the largest component is obviously from subject matter experts across the U.S. academia, from across the national lab perspective. Many of you out there are members of my subcommittee that are listening in right now. And then, of course, from industry, and of course, we've had DOE EM representatives participate, as well as NRC representatives, IAEA representatives, etc. And at the end of the day, this is the process that ASTM pursues, and the standards that are produced are independent and universally recognized standards that the community and international community across the board are free to leverage and utilize. Lots of rigorous checks and balances in that process. We're not going to go through a detailed step-by-step how does that process works, but to put it in perspective, it takes us approximately 1 year to develop a standard specification and maybe about that same amount of time to develop and or identify the associated test methods and testing protocols. So it is a rigorous, extensive, peer-reviewed, independent, verified process for any of these efforts that we do for the various technologies that we are pursuing. It is that credibility, I think, that also bodes well for the community at large when we are trying to introduce technologies that we've developed in the lab and or commercial off-the-shelf technologies that we've adapted and are applying them into the D&D space. And so what have we done to date? Here's just a small sampling of what I mean by some of those ASTM standard specifications that have been developed in the E1003 community or subcommittee. Many of these literally benchmarking the industry now and defining the industry for what those particular technologies are supposed to do when they get into the sites. Those standard specifications go across the broad range of categories for fixative technologies, whether they be decon gels, whether they be permanent coatings like the incombustible fixatives that we deployed into the SRS 235F pump facility, and or now a research activity that we are undergoing and preparing with Savannah River National Lab, our collaborators, and integrating into the D&D roadmap that's getting ready to deploy and be tested, hopefully within the next year, foam fixative technologies. But as we're developing the technology itself, we are also developing the standard specifications with the community in this consensus-based process to outline specifically what it is supposed to do, put that out there, and then we are integrating it and using those particular efforts as the basis for whether it's our test plans that we develop collaboratively. I give a few examples up there, and it's gotten so good now to where the requirement to leverage ASTM E1003 standard specifications for fixative technologies has even been integrated into the request for proposal announcements. So that's showing a deep level of penetration, and DOE-EM really kind of embracing this idea of parallel development of standards and then using those standards to, at least for fixative technologies, to kind of go forward and how to develop them, etc. And they're not stagnant. This is a 5-year periodic update cycle. We are in the process right now on the subcommittee. Many of you, again, I say, are part of that subcommittee in updating E3191 that you see listed there as we move forward with the foaming fixatives. We've learned a lot over the last 3 or 4 years engaging with the site, engaging with DOE-EM representatives on what those specific requirements and safety concerns are, and then integrating that, using that feedback and integrating it into the standard specification. And in this update, we've gone so far as to learn what testing protocols and practices are acceptable with the data for the Insight users and the safety basis personnel, and we're referencing those as well. So this whole thing continues, is a dynamic process, it's circular, and it continues to be updated on a 5-year cycle as we kind of press forward. Again, this model that we are using for fixative technologies could be exported, replicated, and adopted for any technology development program that is being pursued in the D&D space. So what's the way ahead? At least for consensus standards, in my opinion, and I kind of pitched some of this with Rod and others in various venues, I think the way ahead, needless to say for sure, is to obviously continue engaging, and we're in a pristine spot. We're actually leading the ASTM E1003 subcommittee, and we continue doing that for fixative technologies. I would also argue and suggest to those out there in the audience who may be developing other types of technologies that are not fixatives, but are intended for D&D use, to consider placing those and developing standard specifications and engaging the ASTM E1003 subcommittee. Join the committee as the technical expert, and you can start to outline some of these standard specifications as well. So that's the first part. That's a no-brainer. The second part, I think we're at a level, at least for fixative technologies, for a couple of reasons, because it's very mature in the process of our standards development effort, but also because fixative technologies are so widely used across the entire DOE EM complex. We may be able, in my opinion, are at the point where it's time to start exploring the feasibility of maybe implementing a conformity assessment program for fixative technologies. And there's a great example of this being utilized by NRC in their protective coatings for nuclear power plants. And so in their regulatory documents or guiding documents or directives, they outline specifically go to ASTM standard ABCD, and then here are the testing protocols. And that picture to the right with performance characteristics, what they have successfully done with the conformity assessment program, which, as you can see on the bottom, outlines a specific requirement, defines how we're going to determine that that requirement has been met, and how it's going to be integrated, and the quality assurance measures. All of that now is so running so well that the producers, industry, has taken that burden on. So when they produce a product, a protective coating intended to go into a nuclear power plant, they themselves ensure that the standards have been met. So now you have the ideal situation where the cost is being consumed and implemented by the producer himself. And to me, I think for some of those wide-scale efforts that we are pursuing in terms of fixative technologies, PBS, whatever those particular efforts are, fire dam out in the DOE EM complex, right now, if you look at them, we have kind of made sure that there are standards, but the producers themselves have not. I think if we move forward with the potential of at least exploring, is this something viable that we want to do? And then if it is, let's start doing it. I think this is a real big next step up in terms of standards that I would throw out there to those folks to consider. And then lastly, we just have a few more slides. This is one where Melissa has really taken a proactive lead in this. It's her primary research activity. It is the basis of her PhD dissertation, and it was a key critical enabler as well. At the same time, you're doing parallel development of the technology, of the standards for that technology. There are still outdated regulations that we probably need to move forward and provide some empirical data to update those regulations so that the technology can actually be utilized. We brought this up in the D&D roadmap, and it has now been integrated by Evan and Savannah River National Lab in that whole effort. A little sub-bullet in that component that let's not just identify the technologies that we need to focus on in order to facilitate decommissioning, but what other regulations and critical enablers do we need, specifically in the realm of regulations, so that once you do the technology, it can actually be accepted, i.e. the helmet part of the wheel. And so with that, here is the example that we identified in the process as we went forward with the SRS 235F PUP facility and the introduction of the incombustible fixatives. And the guiding document that they utilize in that particular instance is DOE Handbook 3010. And that kind of contains the methodology for the source term formula. It serves as the foundation for any and all safety basis calculations, computer modeling programs, any remediation methods, etc. Problem is, it was the last substantive update to that particular substantive, not just review, but substantive update to that guiding document was back in around 1994. So hell's bells. I mean, that's been a while. So in it, the current version does not account for the use of fixative technologies. In other words, the state-of-the-art technologies that are now being introduced, they can't be accredited, or people can't take credit for the positive impacts they have, because the directive, the handbook itself, doesn't account for them. And so our argument, and what we have started to pursue with Melissa, is a focused effort to provide the research data to turn over to the owners of the handbook to follow up with a substantive update of that handbook that would account for a fixative state, that would account for the positive impacts that fixative technologies have on something like reducing airborne release fractions or respirable fractions, two components that are comprised in the source term formula. And so we said, hey, this is another critical enabler, because the site themselves said, great job on the standards, we trust you, meets that. But even though I'm applying it, I don't really get any credit for it, because I still have to account for the residual contamination as a loose powder, even though we know it is topped off with fixative technologies and immobilized. And this is specifically what I'm talking about. And so we all out there know, everybody knows intuitively, fixatives reduce the risk, they stabilize the contamination. In other words, you should no longer consider any residual contamination that has been coated with the fixative technology as a powder. But that's what they're kind of forced to do now, because there's not this accounting for new technologies that have come into place. And so our hypothesis was, hey, a polymer or a fixative form should be considered in the next update. So instead of using the impact, in this case, airborne release fraction coefficient for a powder, you could use something closer to maybe a metal, or something at least less than a powder, less than a liquid, and much closer to a metal. Granted, it's minimal, but it is a good example of the requirement and the need, in my opinion, of pursuing this kind of parallel development of those other critical updates, other critical enablers, such as updating regulations. And here's what we found. So over the course of the last 2 years, we've been conducting a series of, and as we develop these testing protocols, have codified them into the E1003 subcommittee by producing testing practices associated with it to provide legitimacy, independent review, and peer review. But lo and behold, no kidding, the intuitive component, fixatives reduce risk, specifically by reducing airborne release fractions, has been proven. We have empirical data now that as you go forward, it actually, and this next slide takes a little time because I think it has a video associated with it. Here we go. It reduces it significantly. So you can see, and we took 2 different types of fixative technologies that we have introduced. We put, per the ASTM standards that we developed, loose powder on the particular substrate. Then we put industry-used PBS and fire dam fixative technologies, and we subjected them to the impact stresses outlined in safety basis contingency documents. And as you can see, there are significant decreases, as we all know, but now we have the empirical data to support our intuition. And at the conclusion of this, over the course of year 5, we're going to turn this data over to the owner of DOE Handbook 3010, and hopefully that will prompt or at least facilitate an update. And so at the end of the day, what does that mean? Our closing arguments, that these parallel development of critical enablers, both in terms of consensus-based standards and in terms of empirical research and an investment in research to update regulations so they have the empirical data they need to move forward with that, significantly increases the ability of technologies being developed in the lab, whether it is academia, whether it is industry, or whether it is the national lab system, to transition into and cross that chasm into the end users and workspace as we kind of move forward with this effort. So with that said, we'll leave it up there in case there's any questions. I promised you it would be short and sweet. I think I met that maybe a little right at the 42-minute mark, but I would love and entertain any questions for myself or Melissa.
Hey, Joe, this is Evan at SRNL.
Yeah, Evan.
So I have a question, or I guess maybe a observation. You mentioned the 235F facility, which is in that powder range for ARF categories. The overall D&D scope is essentially to entomb with grout that facility, essentially achieving what a fixative would do by fixing that powdered contaminant with grout. So wouldn't it follow that a fixative recategorizing that contaminant on that scale be nothing new, just a recategorization at a different time, according to the DOE handbook?
So that's a great point. We'd have to look and explore what so this handbook, kind of covers some of the safety. I don't know that there is a time frame associated with how long does it need to fix and hold. Is it indefinitely? So some of the fixative technologies, as you know, Evan, we work with it day in and day out, whether it's a coating, whether it's a foam, they are currently kind of intended to support semi-permanent stabilization, as you know, as we write it in the standard. I think there is long-term testing, like you and I have discussed, for the fixative technologies to see how long can they really kind of hold up to plutonium-238 in the PUP facility before they get degraded and no longer maintain these coefficients we're talking about. We're going to move forward with that and then do a comparative study to grout. So I think there is some additional research to be done. But to your bigger question, I think grout is looked at currently as a more long-term permanent solution, and we probably need to do, but I haven't seen that in the handbook. I can relook it and see if that answers your question.
I think so. Yeah, it's just that if grout didn't do that, there's got to be at some point where they consider the powder to be
powder again,
no longer an airborne hazard, and grout does that.
Right.
So it's kind of an avenue for a fixative to take to get it approved for a lower risk level.
Yeah.
That and the update of the handbook. I mean, yeah, both.
Right.
You're exactly right. So
Okay.
if we can get, to your point, qualify the fixative as a grout alternative, just lighter weight, but still as a grout alternative, and or update the handbook for whatever time period that is. In both instances, they're both critical enablers to facilitating the wide use of fixative technologies across the complex.
Thanks, Joe.
Yep, great question. Thank you, Evan. Anybody else? I don't see who all's on the line, so.
We have folks from DOE HQ, DOE fellows, some people from other national labs. So any other questions before we conclude? Okay, well then, thank you all for attending this Tech Talk. Please visit the dndkmit.org Tech Talk webpage. If you look back at the chat, you'll see the link there. Special thanks to our friends from DOE HQ for joining us today. The recording of this Tech Talk will be posted on our website, and if I also added a link to the newsletter in the chat. So if you sign up to the newsletter, you've been notified for future Tech Talks. Save the date. Our next Tech Talk is October 15. The topic and the speaker will be announced through the newsletter. And again, thank you to our sponsor, the Department of Energy and Environmental Management, for supporting this effort. And thank you again to Joe and Melissa for this great presentation. And thank you all for attending this meeting. I wish you all have a great day, rest of the day. And this officially ends this meeting. Thank you all.
Thank you, Walter.
Thank you.
Thank you.
Hey, thank you, Walter. Bye.